So the next speaker is Bogdan Kolbik. Is a software developer with over 10 years of experience. He is a programming course author. These days, he's developing vehicle routing optimization algorithms using Scala and Rust. 2 facts. Bogdan is reading from 3 to 5 books in parallel, totaling from 25 to 40 books per year. And his oldest project was written on train without internet connection, and it was working for more than 14 years. So welcome on the stage, Bogdan Kolbik.
Yeah, hello. Today I want to tell you about what to do when your problem is NP hard, and you might be like, NP what? So before telling how to deal with such problems, I should tell you what does it mean. And NP in this case means non-polynomial. Wonderful definition. If you didn't know what it meant before, you probably don't know what it means now. And to explain it, I first need to tell you about the big O notation. It's the way to describe algorithm complexity in terms of how many operations it needs to do depending on the input size that we usually call n. It doesn't care about how big these operations are or how small, how much time they take, but it is a nice predictor to tell you how the processing time increases with the increase of the input size. For example, if it's a constant, it's O of 1. If we need to look at every element of our input, for example, take a sum of an array, it is O of n, and the number of operations, if you have twice bigger input, you will need twice more time to process it. There are bigger complexities, for example, O of n multiplied by log of n. It's, for example, a complexity of the quicksort algorithm. And these are very nice complexities. If you have them, you should be happy. There are worse ones. For example, n squared or n cubed. It's, for example, when you need to look at every possible pair of input elements or every possible triplet. And it's much worse. You can see the lines from the previous slide. They're now touching the x-axis because our scale changed. But this is still very good. Everything that is up to n to the power of some constant value is an okay complexity in practice, and it is fine. And it's all is called polynomial. There are non-polynomial complexities that mean everything that's more complex like this than this. This is usually like something to the power of n or n factorial. And we have these complexities usually when we don't have a nice algorithm to solve our problem, and instead we need to look at every possible answer and try it. And it's very slow. It means it's usually impractical to try to solve it when your input size is more than 10 or 20 or something like this. And in the perfect world, you will never need to write algorithms that have such complexities. But we don't live in a perfect world, and there are a lot of business problems that require us to make algorithms with such complexities. For example, the routing problems, starting with the famous traveling salesman problem, where we need to find a loop that visits every city with the shortest possible path, and more complex ways. For example, we might have multiple vehicles, we might have time window constraints for each node, we might have ordering constraints, capacity constraints for the vehicle, and we can have different scales, from something as big as making the routes of cargo ships that go between continents to something small like making the routes of warehouse boats located in a single warehouses. And often it's something like intercity or within the city. So If you make logic for taxi services, it's a vehicle routing problem. If you do food delivery, or if you do ride pooling, something that Moya does. There are other and big hard problems, for example, scheduling problem. Anytime when you have some conditions, like when you want to make a schedule, it suddenly becomes very hard to find a good schedule. And also it's a category where job shop problems fall in, when you have multiple employees or multiple machines that can work on tasks, and for each project it needs to be processed by different machines for some time. You might want to assign the projects to machines at the specific time to minimize the total time needed to fulfill all the project needs. This is project planning software, and it's also an NP-hard scheduling problem. Or, for example, cutting stock problem, where you need to produce some number of items with the minimum waste material. This also is similar to bin packing problem and other problems like this. These are all problems, and they are optimization problems. And if you have one of these problems, I have bad news and good news for you. The bad news: no good solution invented for such problems. We don't even know if it's possible, so probably you will have to look at every possible answer and find the best one. And good news, these problems are not that unique. So they all fall in the category, look at every possible answer and find the best one. And in general, optimization problems are like the field of flowers, where your job is to find the most beautiful red flower, and you have 3 seconds. The time starts now. Time's over. You are not expected to succeed in this task. But you see the problem. You might look at one flower, and it might be nice, but it doesn't tell you anything about any other flower in the field, and you'll need to look at all of them to find the best one. The same with the optimization problem. You can have many solution candidates, you can have one, but to see if it's the best one, you need to look at every other possible solution candidate. And in practice, there are usually more solution candidates than atoms in the observable universe. So it takes a lot of time to look at all of them. And it's nice that we can compare them easily, but it doesn't help us much. And another thing we might notice, that finding the ugliest flower takes the same complexity than finding the most beautiful flower. And basically we can use the same concept. We just need to reverse the objectives. We need to reverse the image of beauty. That's it with flowers. Now we'll look at only the problems. And remember, I said that we can easily compare two possible solutions. I lied. Because, well, it's fine when one solution is feasible, another one is not. But if you, for example, look at the food delivery, we might have multiple objectives. We want to deliver as many meals as possible, but on the other hand, we want to minimize the route made by each courier. We want to minimize the time the food is in the courier trunk so it doesn't get too cold. Probably we want to spread the load among couriers evenly. And maybe we want to have them located near the restaurants in case the future requests come from them. And these are all multiple objectives, and somehow we need to juggle them. And we need to find the best answer that makes it all good. And comparing different objectives is like comparing apples to oranges. We cannot do this. And then the score for each solution is like a basket with apples and oranges. We are happy when one of the solutions is better in every objective than another one. But if one of them is better in one thing and another one is better in another thing, we still need to compare them somehow. So how can we compare apples and oranges? Well, we assign weights. Apples equals k oranges. Yeah, problem solved. And then just make k a configuration parameter, so you can adjust it every time your optimizer produces some garbage output. It works nice. Another way is the levels. For example, kittens are more important than any number of apples and oranges. So if we look at baskets with apples, oranges, and kittens, first we need to compare the number of kittens, and only if it's equals, we can look at the apples and oranges. And we can have weights on different levels. For example, puppies are also more important than apples and oranges, but somehow comparable to kittens. Yeah. In practice, we use 2 or more score levels. We call them hard score, soft score, and some number of medium scores in between. And hard score is anything that we cannot violate because of the laws of physics or because of the laws of the country. For example, your solution is not that good if your food delivery courier needs to travel back in time to make it possible. And such stuff goes to hard score. Soft score is something that we want to optimize, but we don't expect it to be perfect. And when we look at the result score at the end of the optimization, if hard score is non-perfect, we can panic. We don't have any solution. If soft score is not perfect, then it's fine. It's something we want to optimize, but it's okay. Now, with all this knowledge, we can look at possible ways to solve optimization problems. And the first way that comes into mind, because it's a conference in 2024, what about AI? And the short answer is no. If we talk about AI as machine learning and neural networks, many people tried to do it. As far as I know, no one succeeded, probably because there is an easy technical way to see if your AI model produces garbage. And so, yeah, not it. But if you want to impress people, you can use any other way to solve optimization problems and say, this is an AI, and no one can object. So you can use it. Another approach, if you don't look at AI, the next thing we should do is to ask ourselves, what do people in universities do to solve such problems? And yeah, there are many scientific papers for each kind of specific optimization problem. Usually they start with describing the problem in words, then with references to previous papers regarding the same problem, and then they write something like this, and the paper ends. Yeah, this is the mathematical description of the problem. And if you come up to the authors of this paper and say, well, yeah, but how to solve it? They tell you, that's it, that's the solution. What else do you need? And the context we're missing when we are confused by this is there are algorithms that are pretty good at solving problems that look like this. We want to minimize or maximize some formula with some constraints on the variables. And you see, it's very similar to our scores. If your first line is our soft score, and the subject stuff is our hard score constraints, it seems like what we are trying to solve. Optimizing it still an NP hard problem, but in practice it gets solved very fast. It's much harder if you say, by the way, some of these variables need to be integers. It's much slower, it's not that good anymore, But still, there are many tricks people came up with to make it faster, so we can use it. For example, let's see at the knapsack problem, where we have a knapsack with some capacity, and we have different items. You can see I'm not covering it. That each has weight, and the profit we get if we take this item. So probably it's a problem about stealing. And we need to find a set of items we can take so their weight is within our capacity, and we want to maximize the profit. If we want to use mixed integer program for solving this thing, we define 3 variables, 1 for each item, and it's a Boolean item. It's 1 if you take the item, 0 if you don't take the item. And then we need to solve this problem, where we maximize the profits multiplied by whether we take the item, with constraint that the sum weight is less or equal to capacity of our knapsack. This way we can solve optimization problems using these solvers. And this means we need to find a MIP solver to do all the number crunching for us, where MIP is called mixed integer program. This is a term you should remember if you want to use it, because it's the way how you find all these solvers. I can suggest you to start with the skip. It's a nice open source, good solver. It's not as fast as commercial ones. There are also commercial ones. But you can start with it and see if the speed improvements is worth paying the license cost. And what you see here, it's not the skip logo. It's the number of, it's the list of the modules implemented inside the skip. Most of them are different tricks they did to make integer programming optimization faster. And I'm showing you this list to discourage you from trying to implement your own MIP solver if you still want to do something else. For example, solve the problem you had in the first place. It's just too huge using existing ones. And yeah, as a conclusion for MIPS solving, you can reuse problem definitions from scientific papers. You don't need to implement stuff. But the problems are not every kind of score and constraint can be done. For example, if you remember the traveling salesman problem, it's easier to define the shortest route that we try to minimize. We can also easily say that we can enter each city once and we have to leave each city once. But it's much harder to make a constraint that makes sure it's one big loop joining every city and not multiple small ones. And it's still NP hard. The fact that we are outsourcing all the optimization to another tool doesn't suddenly make it fast. With big problems, it will take a lot of time to optimize. And Solver is an external tool. You either need to call it over network, or you need to somehow pack it and deploy together with your application and then call it. And it means you need to decide what to do if it takes too much time to solve it, what to do if it returns errors, and it all adds infrastructure complexity. Another more programmer way to solve it is local search-based meta-heuristics. And for this, we can notice that if we change our solution candidate a bit, the score change will also be limited to the stuff we changed. Like on this picture, if we look at any green pixel and then look at neighboring pixels, they will also probably be green. Yeah. And we can make a logic based on this. So we can imagine our whole solution space as an n-dimensional plane where our solution candidates is a dot and we can move over this plane. Don't worry, don't need to implement n-dimensional planes, but local search algorithm in general looks like this. We take any candidate solution, then we apply a move that modifies it a bit, check the score for the new moved solution, and see if it's better. If it is better, then we are happy. We found a new best solution that we can return in the end. If it's not, that's where the problems start. And I can show it to you in the picture on this unrealistically simple problem where we have only one variable that can increase or decrease. So we have two possible moves, step left and step right. We have some current state, we consider other states. We move right, our score increased. Nice. We move right again, our score increased. Nice. We don't know yet that we are trapped, because as a humans looking at this chart, we know that there is another point with much better score. But the program that's trying to optimize it see only current state, and it also sees that any move it can apply right now will decrease our score. And even if we allow decreasing score and we go somewhere else, there is a big chance we will get back to our local maximum. So it works as a gravity well. And we need different tricks called meta-heuristics to try to escape local maximums and to search for a global maximum. These are the most popular ones are simulated annealing and taboo search. For example, in simulated annealing, we consider only one move per step, and we either take it or not. And we might take it even if it makes our score worse, if it doesn't make it too much worse. For example, this one is fine, this one is not fine. Yeah. And what is considered fine is different depending on the time during optimization. So at the beginning of optimization, we can accept very bad moves, and at the end, we are accepting only the moves that increase our score, which means at the beginning, we move randomly around the search space, hoping to get into the gravity well of the best local maxima, of the global maxima, and in the end, we go inside the local maxima and find our best solution. Another way is taboo search, where we consider multiple possible moves at the same time and pick the best of them, even if it makes our score worse. And the trick is the places that we just visited or visited recently, the so-called taboo zone, and we cannot accept moves that go back into the taboo zone. So we need to accept the best move that doesn't go inside. And in this case, it will still push us to the right. So with taboo search, because we consider multiple moves at the same time, we will get to the local maxima much faster, but then we hope that this taboo zone will push us out of the local maxima gravity well and to the best global maxima gravity well. Well, one way or another, we might find some path to our global maxima, and you would say, hooray, but the local search cannot say it, because unless your specific problem shows you that it's impossible to have the better score than the one you have right now, there is no way to know whether your solution is best or not. So local search will actually move around the search space until it reaches deadline, and then it will just return the best solution it found so far. Yeah. If you want to do it in practice, you can use the library called Optaplanner. It's nice, it implements many different meta-heuristics, and even if you're not going to use it, it's nice to read documentation for it, because it explains meta-heuristics that you can then implement yourself. Because They're very simple. The most complex part there will be implementing the score calculation, and there you should take care to make your score calculation incremental. So if you change only the part of the solution, it means only the part of the score changes. And if you don't recalculate the score completely, but only the changed part, it will make it orders of magnitude faster. And in local search, it matters because we want to check as many possible states before our deadline reaches. This is also the reason to use the programming language that is faster. For example, in Moya, we use Rust for this stuff. And conclusion for meta-heuristics, you have a lot of control over the termination. You can have multiple different conditions when you terminate and when you don't. You can have control over different problem-specific tweaks, pre-optimization phases, and stuff like this, and everything can be as simple or as complex as you want it. The negative parts, you have to write code. And you never know when the solution is optimal, and anyway, it's still NP hard. So finding the best solution will take a lot of time. I want to tell you different tricks you can try and that make your solving faster, disregarding on which method you try to implement and use. One of them is put the constraints into the model. For example, we can look at the 8 queens problem, where you have a chessboard and you need to place 8 queens on it, the way that they cannot hit each other. And as a lazy programmers, we don't want to think. We instead make that program that considers every possible position and returns all of them that are satisfying for us. But what does every possible solution mean in this case? For example, we might have a Boolean for each cell. Well, we have a queen there or not. And in this case, our solution space is 2 to the power of 64. It's 10 with 19 zeros. That's a lot. But then we can think, wait, we can have only 1 queen in a row. We cannot have 0 because it means somewhere we will have 2 queens, and we cannot have more than 1 because they will hit each other. So we can change our model to store the position of a queen in each row. And this means that our solution space is 8 to the power of 8, and that's much smaller. We can then think that we can have only 1 queen in each column, and it means that we can only have permutations of numbers from 1 to 8 as our model. And in this case, our solution space is 10 to the power of 4. It's 15 zeros of difference. In any case, it's the same idea. Let's try every possible combination, but 15 zeros of difference is a difference between fairly easy and impossible. And as a bonus, in the last case, you don't need to waste time validating that you have only 1 queen in a row or only 1 queen in a column, because it's already built into your problem model. Another way is to split the problem. So if we know that our calculation time grows very fast with the input size, it means that solving multiple smaller problems is much better than solving one combined problem. And for this, you need to look at your business problem to see how you can split it into hopefully independent sub-problems. Usually it's something like by location. You don't need to optimize every city in one problem. Or by time, especially if you have something like service hours. It means everything that goes in different days is independent. Or you can have separation by stages. This is not that dependent. For example, you can have different optimizers for big and low-level decisions. For example, one of them is assigning containers to cargo ships. So you want to decide which container to deliver with which cargo ship. And another optimizer is deciding on the position of a container within every specific cargo ship. In the result, it might produce not as good solutions as when you are optimizing everything at the same time. But having an okay solution now is usually better than having the best solution in 1,000 years. And with problem sizes, 1,000 years time is sometimes a very optimistic estimation. And because of this, another trick, don't. Just the fact that you have an optimization problem doesn't mean that you need an optimization solution for it. Sometimes having a simple thing that produces okay-ish solution is cheaper than having a complex thing and supporting it with a separate team of developers. Yeah. So as a general conclusion, I have some news for you. First, if you have an optimization problem, it might seem scary, but there are ways to approach it, just need to search for them. And another good news, if you don't have an optimization problem, but it seems interesting, well, there are jobs that require you to solve unsolvable problems. Just need to search for them. Yeah. Thank you.
Thanks, Bogdan. So, do we have any questions, basically? Yeah, good. Just take the mic.
Thank you, Bogdan. Can you please tell a bit more about this MIP stuff? So there was an image with the many different algorithms. So it's kind of algorithms library, and if you have some problem, you can go there and find something that fits you. So what is the output of this stuff? Do they give you some code on some programming language or approaches or what?
No, you define the problem in these formulas. There are even some standard ways to define this. So basically you generate the formula you want, you generate your constraints using your input data as constants in this MIP stuff, and you generate some variables that will be later used as your results. And in the end, it tells you which variables you need to take to have the best solution possible. And you then just convert these variables into your result. For example, in knapsack problem, all the profits and weights of each item, they go as constants as input to the MIP solver. And the variables is Boolean, whether we take each item or not. And then it's obvious how to take the results of the values of these variables in the result and how to turn it into your problem solution. Did you
Does it give an answer for the problem or an approach how to solve it? This is what I can get.
It does give an answer for the problem.
So it's kind of complex algorithm that you can feed with your task in some standardized way. Got it.
Anyone else? Okay, nice.
Yeah, thanks for the speech. I actually, regarding the meta-heuristic approach, isn't it the same one that we use to optimize the weights of the neural network, as far as I remember, or no? Do we use the same meta-heuristic approach to optimize the neural network to give us the score that we want, to give us the answer that is closest to the score that we want? Or do we, because as far as I remember, we use some kind of gradient search with steps. So yeah, that's my first question.
Maybe. I never tried to optimize neural networks, so I cannot tell you.
And the second, I actually had one problem essentially when I was working. I had to solve one problem, which was essentially finding either the longest path in the graph or finding a path over specific length. And as far as I remember, this is an NP hard problem, so I had to go for a partial solution. So my question is, how would you approach to solve it?
First, I would try to understand if it's a well-known problem and find the name they use to describe this when it's a well-known problem, and then look at for scientific papers or even for books, because there is many learning materials about this solving in general, but there are also many learning materials on every specific problem and how they use different ways to approach it. So basically, I would start thinking at the last moment. First, I think first I check if someone already solved it.
Okay, yeah. Thank you.
Thank you.
So, any? Okay, nice.
Hello. Usually when I was looking for O notation, it was totally about code, a number of if statements, etc., algorithms. And I was thinking about, it seems like very useful stuff and can it be applied for more practical tasks? For example, as me for DevOps, I don't know, is it efficient to, I don't know, automate or make it by hand, something like that?
Well, I checked the wiki page on big O notation today, and it's used not only for algorithms, but somehow in the mathematics. I didn't check how, but looks like it's useful not only for us. And yeah, even if you do it for DevOps and in practical stuff, you can estimate how much time it will take, and it will easily show you to cut off some of the possible algorithms because they're too slow.
Okay, thank you.
Thank you.
Hello, thank you for your presentation. Today is like 2024, yeah, and everyone talking about AI. You also done it, but it looks like I hear at least that you do not believe in AI in these NP problems. Can you describe a little bit why AI struggling in it, or maybe do you believe that somewhere in future AI can be useful for these problems, or it is dead end for AI? What do you think?
Well, my personal thoughts is that this problem is not just not good problems for AI. For example, when you have a lot of constraints that are somehow deep and complex, it means that if you generate just a random number with, okay, let me say differently. Two possible problems. One of them is traveling salesman with time windows. Another one is looking at the picture and seeing if it's a cat or dog. When you look at the picture and try to say whether it's a cat or dog, you can make a random answer and it will be a feasible answer. It might be a bad one, but it's still a feasible. With traveling salesman, if you make a random answer, in the most cases, it's just infeasible. So it's much harder to train when there are some internal logic, internal consistency that you have to follow, and AI, like neural network, doesn't know about it. And on the other hand, these optimization approaches work nice enough because you can compare two possible solutions for traveling salesman problem and find out which one is the best. When you compare two possible answers made by AI, to know which one is better, you need a third AI that is an oracle. Yeah. So maybe there were nice approaches that don't try to use AI to find one global solution, but instead have an optimization problem that is backed as AI as a sub-problem. when we try to decide which next step is better to take, and AI is deciding this, and then there is a big smarter or dumber thing trying to turn it into a big solution. These things look promising, and maybe it will be done like this. But yeah, so far no one succeeded.